So this is the third Polaron talk in a row. And the talks were not coordinated in advance, so you're going to hear certain things again. I'm sorry for this. But roughly speaking, I want to combine two ideas from the previous talk. So I want to talk about mobilities, and I want to talk about determinants for fermions. And yeah, that's so the situation was that the calculation for the Fröhlich Polaron, the mobility was running, and then it took several months on a supercomputer to get very precise data. And so in the meantime, you start thinking, you say, well, what about fermions? And so then you know that determinants are possible, and so you start thinking, and then you think, well, okay, I have a new master student, so maybe it's a good project. And then, as always, things are more difficult and take longer. And ultimately, I can only give you a status report now because of other things. Okay, so the question is, I have an impurity in an otherwise non-interacting Fermi bath. We'll take it to spin polarized here. And the question is very simple. How does a particle move in a fermionic reservoir? And so if you have a cold atom background, you think of the Fermi Polaron with resonant interactions as in Chris' talk. And essentially there is almost nothing in the literature. There's no experiment. There is almost no theory. Could be done, I think, but has not been done, maybe with the Rydberg. And then the other system that comes to mind is, so this was the resonant Fermi Polaron. Yeah. So we've seen this in the previous talk. I don't want to spend time. And so the other system that I know was about ions in helium-3. So in helium-3 being fermionic, which was presented by Nicolai. And so we know that these electrons, they repel the helium atoms, and the effective mass is enormous. It's 200 times the bare mass of a helium. And so there are some links with orthogonality catastrophes. And if you look at, so people define the scale T0, which is the Fermi temperature divided by the effective mass of these ions. And this is orders of magnitude, factor of 100 smaller than TF. And so, and as Nicolai explained, this problem is in the strong coupling regime, so the effective coupling G is of the order of 25, and that means that even at high temperatures, this is definitely already strongly overdamped. And if you look at the experimental data, which Nicolai also showed, then, actually there is a little difference here in what I present. So Nicolai actually only showed data up from here and down. So the first thing I found was if you look at the mobility, the temperatures of the order of TF, then actually it goes down. And this was explained in this paper by Kondo and Soda from '83. And they neglect the recoil. And the formula you see here is that mu goes as the residue, so z of t squared. And z of t goes as t over tf to the power 2 times v naught, which is roughly the S-wave scattering length times density of state squared. So this is essentially the phase shift. So this is orthogonality physics that sets in. And then what is very remarkable is that the mobility is constant, or perhaps logarithmically increasing, but definitely very flat. And so I took results from different papers. So here you see essentially over this parameter regime that for positive ions, this is really flat. Also for negative ions, it's roughly flat, but sometimes experiments are more difficult to interpret because there is some remnants of helium-4 left. And then this remains flat until you are, here you see a small increase, log T over T naught. But this is nothing, this is roughly constant. And then until you hit Tc, helium-3 becomes superfluid, develops a gap, and then the mobility shoots up. And all of a sudden it becomes quasi-ballistic motion. This is surprising. So this was hard to explain. Okay, and Nicolai presented his theory, which is summarized on this scale, on this slide. And so if you look at, so I'm very quickly going over it, and so the mobility, if you write it in the Drude form, then we know it's diffusive motion as long as omega is smaller than the scattering rate gamma. But the experimental observation is that mu is constant. Gamma, constant. Or gamma here interpreted as the width. And that is true for temperatures much smaller than gamma. And this is now definitely at odds with Monte-Carlo limit, which says that the thermal wavelength should be much smaller than the mean free path length, or as Nikolai explained, it's really roughly the same as saying that scattering time has to be much larger than 1 over temperature. And so you have a problem, because if you want to extract m and gamma from dc of mu, then you could say, well, if this is constant and m is constant, then gamma has to be constant. But this violates sooner or later this. On the other hand, you can make the interpretation that Nikolai made and saying, well, we keep the Planckian bound, so the tau remains 1 over t. So scales with temperature, and then it follows that you must have an effective mass that essentially diverges as 1 over temperature. But Nikolai argues that this is the correct interpretation, because if you go to the superfluid regime, you see this appearing with a huge mass. Okay, so one goal would be to provide some more data to such systems and test these kind of interpretations, and to see if we can substantiate these theories. All right, so what do we do? So we consider a Fermi polaron in the overdamped regime. That means we take some potential here, soft sphere potential. So there is some amplitude V naught and a range R naught. Yeah, and then we tune the parameters such that you have many angular momentum states. Okay, so and then probably it doesn't really matter what the shape of this potential is, you're just in an overdamped regime. Okay, some plots. So if you solve the scattering problem, this is a two particle scattering problem in vacuum, essentially, just to get an idea of what parameters you would expect. Then you see the effective coupling G, and if you tune R naught or V, yeah, you get different curves, and you see, well, strong coupling regime for one is around here. But if you want to have very strong coupling, you either need a very large range or pretty strong interactions. Now, these plots, they are very, very, very hand-waving, because the energies in our true many-body problem will be different. We have reduced mass. But somehow what appears constant if you do this kind of analysis is the number of partial waves that are involved. And so typically for R naught, you have the order of 6, which is essentially as far as we can go. It's of the order of 20. I assume this will be good enough. Okay, so this is now the setup. We have this soft sphere potential. We have non-interacting fermions. And we want to compute, on the one hand, current-current correlator function or momentum-momentum. On the other hand, we also want to compute at 0 temperature effective mass and Green's function, and see if ultimately this can be reconciled. Okay, so we have two different codes that were written. The first code is a Green's function code for 0 temperature. So we want to compute the Green's function of the impurity at 0 temperature when it's dressed with the fermionic bath. And so this goes as follows. So we have a backbone line for the impurity, and it interacts with the bath. And then we compute the determinant for the scattering vertices of the bath. Yeah, this sums up overall topologies in order 3. And so the weight is very simple. So it's minus V naught to the power n, the product over all the impurity lines, and the determinant that you have here. Yes, so we have to use our tau representation here just to have it. Yes?
Sorry, why do you have two outgoing lines in the determinant?
The interaction is density-density. And so it's a local interaction of density-density type, so we have an in and an out. Just like in-out here, density-density.
Same way, two out.
No, it's one in, one out. It's wrong.
Okay, that makes sense.
This is wrong, sorry. Okay, what is special? Thank you, I will correct it. What is, so this is ultimately a Ruptsov algorithm. Yeah, the normalization here happens through the zeroth order diagram, which is the non-interacting impurity Green's function. So this is not a partition function code, yeah? Unlike the one for later for finite temperature. Okay, we don't have to use CDAT here. No, that's a simplification for polarons. you just have to compute the determinant and not do anything recursive. It's a great simplification. Okay, this thing works. All right, now I spend a lot of time analyzing how to do this, and one thing I figured out is that it's extremely important to compute the non-interacting Green's function extremely accurately. And so I looked very carefully on how these things are derived analytically. And ultimately, you can write the lesser and the greater Green's function in terms of some error functions or these W functions. But these things, you know, they can be ugly. So you have these factors that can be ugly, especially if tau is very small and r is large. And these functions, they diverge. Yeah? So if you look at r equals 0 and small but positive time, these functions diverge in 3D. And so it turned out it's very important to do this very carefully. And definitely there is room for optimization here, because I currently spend 50% of the time computing such Green's functions and not on the determinants. But I somehow figured out that you know, to do these things accurately, you improve the sign. It was one of the mysteries that I still do not fully understand. But if you do it very well, then you have no choice. Yeah? So that's the message. You have no choice. You have to take these things here very carefully. You have to treat them very carefully. For the impurity, it's the formula that you saw on crystallites as well. This is standard. This one is not causing any headache. All right. So what about the Green's function code at 0 temperature? Now, there are a couple of tricks. So one is an energy shift. So you can shift the spectrum, and you usually do this because, you know, if you form a polaron, ultimately the Green's function will decay exponentially with a slope which is the polaron energy, if the polaron is found. And so you want to tune your system such that you stay just below this polaron energy, and that means that everything is exponentially decaying and is convergent. On the other hand, you don't want to be too far away, otherwise this decay is too fast and you lose resolution. So this is a classical trick, but tuning this energy matters. And then there is, of course, an alpha trick, which I also had to figure out in this case. So you can do the attractive interactions don't have this minus sign here. The repulsive ones would do, but with an alpha trick you can get rid of this. Yeah? So this is simply done in the usual way by shifting the diagonal of a determinant and compensating for it in the impurity Green's function, but that's just a total overall shift. This is roughly Hartree energy-like that you shift. Yeah? This is shifting the diagonal of the determinant in the usual way. This is a good trick. Okay, now the thing that extremely surprised me is the sign. I looked at the sign as a function of R0 for some interaction here. And what you see is, for repulsive interactions, equal mass. All my data are now for equal mass, so not relevant for helium-3 ions. And you know, the sign is incredibly high. The sign here can be 0.55, which is not a sign problem. And this surprised me, yeah? And you look carefully and you improve the G0 and the sign gets better and you start thinking, what's going on? And ultimately, I don't really know. But note that this is a single determinant. The sign is coming from a single determinant. And in continuous space, apparently not a problem here.
That's for a particular order?
I will show you. I have data per order. I mean, of course, yeah. So this is what you asked. So when you look at the histogram of how often you're in a certain order, in a regime that is already a little bit interacting, so you see that this here goes up to orders 50, 60, and the sign goes down, of course, with an order. But in this case, it's not a catastrophe. And this surprised me because, you know, we now go towards 200, 300, and okay, this is not supposed to be possible, yeah. I mean, at that point, if you want to do a continuous field theory through many, many body, then you know, the recursive relations will become impossible, not this determinant. But okay, let's not dream about this at the moment. Okay, now there are some like sign games, yeah? So ultimately, you know, the alpha trick for repulsive interactions is always a winner, so we will do it. You may have to tune a little bit the value of alpha, but I always take it to be 2 and seems always to be reasonable. But then, you know, there is this parameter E0, and you know, how far you detune away from your ground state energy, And for difficult regimes, so say when R0 is large, this is tricky, because on the one hand, you want decay, so that you can actually measure something and not go to too high orders where the sign ultimately will kill it. On the other hand, you want good resolution. So if you pull too hard on E0 and you make it too close to the true energy, you win, of course, because you have much better resolution, but you fall off the cliff because of the sign problem. On the other hand, if you tune it too far away, you kill the sign problem, but you lose every signal, roughly, accurate signal. And so it's a very tight balancing game that you have to find, and there is some issue there that is not fully understood at the moment. Okay, let me show you some results. So this is the Green's function at 0 momentum. So the log of it as a function of time, and you see that this is nicely, this is like 8-hour calculation. Single node gives you very good convergence, and with some, you can fit this reasonably well. Of course, this fitting is always a bit of an issue. Where do you start? And that influences it. But you can read off a z factor and the energy. You can tune a bit better in this case. Okay, if you look at the z factor as a function of R0 for fixed V0, then you see that for 4 here, I mean, it's still a reasonable quasi-particle, so it's 0.6, something like this. But if you go to R0 6, definitely the z factor becomes very small. Yeah? And so whether it is, this is like the regime where we would like to go to. So here you would become strongly overdamped, probably. And that would be the interesting case to see what remains of Drude theory, what remains of all these interpretations, and so we'll see. Okay, this is the energy. So the energy is pretty boring for the same parameters, so it just seems to go down in this fashion. Okay, and that's now the end of the good news. So if you go to R0 6, which is this interesting case, and you look at the Green's function, then all of a sudden you see it becomes like noisy. And it's very hard to improve, and this becomes very difficult to fit because this keeps curving, and you never know when it's really going to set in, and the sign problem is now there, and it's a very low z factor, yeah? And it's this low z factor that gives me a headache, because this low z factor tells me how long this goes on, and it gets difficult. And I must say I have not solved completely this issue. However, there was how to go beyond the problem of low z factor. So there was a very elegant solution that was in the long Fröhlich-Polaron paper from Boris Nikolai and Andrei Mishenko. And the idea is that instead of doing the Green's function, you address it with particle Hall fluctuations at the endpoints. And if those are conjugate operators, then you know that ultimately this whole object will decay with the same energy, but the z factor will be 1, because the sum over all the sectors that you have here must sum up. So all the z factors for each one separately, you sum them all up, it must go to 1. All right, and so there is some hope that if you do this, still with a determinant, you might solve the problem of low z factors. And it did it wonderfully well for the Fröhlich-Polaron, because Nikolai showed you data where the z factor is 0.001, and he measured effective mass of 6, 7, and more. Okay, this is still compatible with fast updates, so you spend 2 days to compute still, to program this with fast updates, you debug, blah, 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 so it's about 2 days. And you have to make sure that these are not linked, so you put a 0 there. And then you look at it, and it seems to work. So this is for R0 equals 3, so the old data is the green line. And the purple data is the new one, summing over all the particle Hall sectors. And what you see is that, yes, ultimately it starts decaying with the same slope as the Green's function, but it's noisy, and it sets in a bit later. But apparently, I implemented it correctly. And okay, I shifted here still with my usual shifts, E0 and the Hartree energy. So you see something. Unfortunately, it doesn't really work because of the sign problem. So for these cases, the sign problem is back. And it's very unfortunate because the sign, if you add these particle Hall fluctuations, it just drops very quickly to 0 already. So R0 equals 3 is the last one, but the sign is already 0.1, and then it's roughly 10 to the minus 5, the sign. And the number of particle Hall pairs on the endpoints is very large. it's 15 to 20, and so yeah, I was thinking if you could do an explicit summation over those to have a sign cancellation, but for 20 it's impossible. All right, so unfortunately this doesn't work, and I have no good way to solve the low z problem at the moment. I see only one thing, which is a flat histogram, which I absolutely dislike because I think you bias yourself easily with these things. Okay, so but unfortunately this is a work in progress, or let's say it's a work in progress like this. Let's hope something works out. But currently it's unsolved. Yeah, we will need some blessing to find it. Okay, now let me show you some data for the effective mass for R0 equals 4. So I computed it for different external momenta. Okay, this is reasonably well fit with the parabola, and for R0 equals 4, the effective mass is 1.2, so very low. For R0 equals 6, I cannot tell you the effective mass. It's probably impossible at the moment. Okay, now, all right, as Chris explained, the idea of fast updates and the proper zeros makes an extension to a T matrix called possible. I don't want to say much about it. Okay, so this is currently what we have for the zero temperature. Now what about finite temperature? So for finite temperature we use essentially the same trick, also with the wrong arrows, but now the diagram of the impurity lives on a ring, a periodic function in beta from 0 to beta. And now there's a subtle difference. So now the normalization is through the partition function. Yeah, so this is slightly different. You don't normalize via the zeroth order diagram, but you just divide by the number of independent samples ultimately. Which also means there is not really an energy shift trick here. But it's not so much of an issue. Alpha trick is possible. Okay, and the computation of the Beer-Green's function still needs to be done very, very carefully. You have the same effect on the sign. And so, okay, the computation of the Beer-Green's function is done by an interpolation on the difference between the finite temperature and the zero temperature one. Okay, all right. Then you need some estimators. So we need one for the kinetic energy. So for the kinetic energy, essentially, you look at all the intervals and you see how far a particle has diffused in such a time. And then there is an overall constant that you have to add that depends on the number of intervals. And so people who did helium-4 or path integral Monte Carlo will recognize that this is the same estimator, except that there is an n here. Because we, yeah. Okay, and then the current or momentum. So Nikolai had an easy one for momentum, because the basis was momentum. Now the basis is real space. But it's still possible to derive the estimator, and so you still have this function f, and then you have to, per interval, compute, so the mass of the impurity times how far the impurity has moved as a vector times this function f, which is the Matsubara frequency times the time difference, but then in this combination divided by omega m. And then there is a second term, and in the derivation this one is found if you the two vertices that you add, if you add them on the same interval or on a different interval, these are these two terms. Okay, that seems to work. And so the normalization is that for Matsubara 0, this is normalized to the mass, and the integral has to be, okay, I forgot if it's the kinetic energy or half the kinetic energy. Okay, and then so we collect these data, and then we send the data from Matsubara to Andrei, and then it's a black box, and then it comes back as conductivities. And currently I cannot really make much about this. I can only show you the data which I received yesterday. And so for R0 equal 4, where I would assume we still have a reasonable quasi-particle, so Andrei's data look like this. And I did now a PowerPoint or a keynote fit with the Lorentzian, and I came up with this. And so it deviates a little bit.
What's the x-axis?
Frequency, real frequency. This is real part of sigma, and this is real frequency. And so, I mean, this is a low value. Yeah? So this is not where mu is very, very high. Yeah? So the issue that Nikolai mentioned, that you can have a very sharp, narrow through the peak is possible, but here the temperature is, beta is 4. Fermi energy is 1. Okay, and now so for R0 equals 6 and 7, we also did the analytic continuation for different temperatures, and I must say it makes no sense to me at the moment. I can only show you, and what you see is that the mobility is either constant or goes down as a function of temperature of both R0 6 and 7. But arrow bars are, according to Andre, rather large.
But you showed us the same for bubbles. You even explained it.
Say what?
You showed us the same for bubbles and even explained it.
But
For
here
the
the
bubbles,
mass is
it was
one.
just going down, then almost flat.
But the mass is 1 here. I mean,
The bare mass is 1.
but the effective mass, I can't compute it. I mean, I have a problem with the sampling. I have a bimodal distribution of centered at the order 1 and one at order 500, and that just tells me something is not okay. Yeah? So my E0 is above E probably, and the low Z is killing me, and I cannot really solve it for R0 equals 6 at the moment, and it's a problem. Yeah? It's really a problem. So if I truncate a little bit, it looks like effective mass is 5, but I have not said that. So it's not that my effective mass becomes very large, but no, it could be completely off. It's very tricky at the moment. Okay, and if you look at it in more detail, so this is for R0 6, and these curves are for different beta, 1, 2, 4, 6, 8. And so the DC value of the mobility, you see that it goes down. And for lower temperature, it starts to it's not even a maximum. And it's even more pronounced here for R0 equals 7. According to the analytic continuation, true or not true, I have no idea. It looks like that a maximum develops at finite frequency. But in Nikolai's talk, it was the other way around, right? So if you go to higher temperature, you get this behavior, not if you go to lower temperature. So it's a bit of a mystery, and I have no idea what's going on. Okay, and I think, yeah, that's it. So, okay, in principle, we have almost everything except the problem of the small z factor, so let the game begin. I still don't understand why the sign is so good, so, I mean, I can go to these extreme high orders, and I don't know really why. The potential matters to some degree. It's the potential that sometimes kills sign changes. Why? I don't know. Maybe it's still not good enough. I don't know. And so, yeah, the question we want to address ultimately is what about mobilities in the beyond quasi-particle regime, thinking of this helium, thinking of orthogonality catastrophes, maybe Rydberg's later in Fermi Polaron. Yeah, these things are also kind of important in the context of these 2D materials. Excitons and tryons are heavily studied at the moment. And of course, the real goal would be to go to Keldysh if it's possible. So computing the diffusion constant then probably on Keldysh contour. And yeah, but first you do this because you still think that the sign problem is probably better and you want to get a feel for what's going on before doing Keldysh. But yeah, ultimately I want to give it a try and we'll see what happens. Of course you will get convergence issues and this is what scares me. And yeah, if the determinant is so good, then of course you start thinking or dreaming about continuous phase quantum field theories. But this is dreaming at the moment. Okay. And if, I don't know, is Giuseppe here? No. Okay, I had a slide for Giuseppe on our other work, which is on, with machine learning, we managed to learn the phase diagram of the classical XXZ model on pyrochlore, learning symmetry-broken nematic phases, usual Heisenberg antiferromagnet, learning spin ice, and another spin liquids thing that is a pseudo-Heisenberg antiferromagnet. And we learned spin liquids, classical spin liquids via local constraints. And, okay, coming out soon. All right. In agreement with previous analysis, 1-to-1. All right. Okay, thank you.